Next thing on the what you need to know list says understand how solutions are formed. And you've encountered many solutions in your life and you've never actually thought about it on a molecular level. Like when you're putting sugar in your tea or your coffee, or if you're putting salt in your water in order to make pasta, you're just assuming it's all going to dissolve and no big deal. But what is actually going on that molecular level? What's happening is that the bonds that attract the solute particles to each other have to be broken. And the bonds that attract the solvent particles to each other have to be broken. So that association, those attractions have to be broken. And then you have to form new attractions between solute and solvent. So what I wrote over here was that you have to break solute-solute attractions, and then you have to break solvent-solvent attractions, and you have to create new solute-solvent attractions, okay? So break solute-solute, break solvent-solvent, and then create new solute-solvent attractions. All right, so what are these attractions? It depends on what the solute and what the solvent are. So we're just going to assume an aqueous solution. So we're going to say water is my solvent. Now, what happens when you put an ionic compound in water? Ionic compounds will basically separate out into their individual ions. If they're going to be dissolved in water, they're going to separate out into ions. So for example, if you put sodium chloride in water, if you just throw some salt in water, you know that it's going to dissolve. But why is it dissolving? How is it dissolving? This is what's going on. So we already know that sodium chloride is this. This is sodium chloride. Separates out into ions, a sodium ion and a chloride ion. And then the water molecules start to surround the ions. So we call them hydrated ions. All right, remember what water looked like from earlier chapters. Water was bent angular. Oxygen is more electronegative than hydrogen. This side is partially negative. These sides are partially positive. So when you're looking at the polarity of the molecule. So these are ionic compounds that can separate out into ions. And now the water molecule, the partial negative portion of it, is going to be attracted to the positive cation, the sodium ion. So your water molecule surround the ion like this. So the oxygen part that is partially negative is attracted to this sodium positive ion. Well, then which part would be attracted to the chloride? The partially positive hydrogen. So all the chlorides will be surrounded by water molecules this way. So we call these hydrated ions, and that on a molecular level is actually what happens when any ionic compound is dissolved in water, separates out into ions, and this is what happens. You get these hydrated ions. Well, what about a covalent compound? Something like sugar. Sugar is a very covalent compound. And for those of you who are going to be going on into intro to organic and biochemistry, you're going to be able to draw the structure of sucrose, no big deal. But I'm not going to bother with the structure right now. I'm going to tell you that sucrose has a lot of OHs in it. Lots and lots of OHs. Do you guys remember hydrogen bonding from a previous chapter? Hopefully, yes. So what happens with covalent compounds in water? You form hydrogen bonds. So if a covalent compound if it can hydrogen bond with water, it's going to be soluble in water. If a covalent compound can't hydrogen bond with water, it tends not to be soluble in water. Okay, ionic compounds, hydrated ions, no problem. As long as it separates out into ions, yes, they'll all be soluble. But covalent compounds are tricky. For example, an oil molecule, no potential for hydrogen bonding there. There's no hydrogen bonded to an FON. So oil will not hydrogen bond with water. They just separate out. They won't form a beautiful solution. But sucrose, glucose, a lot of molecules that have all those OHs will hydrogen bond with water. And if it can hydrogen bond with water, it will be soluble in water. Same scenario. You have to break solute-solute hydrogen bonding, break solvent-solvent hydrogen bonding, and then you're going to be creating solute-solvent hydrogen bonding. All right? So that's how solutions are formed, whether it's an ionic compound in water or a covalent compound in water. What are the factors that affect solution formation? Now, those are in your what you need to know list. The three factors I pointed out are state of subdivision, degree of agitation, and temperature. Let's go through these. What do I mean by state of subdivision? That means how much surface area do you have? How much is it mashed up? For example, let's say you had a sugar cube versus powdered sugar, and you have the exact same mass of both and you put them in water. The powdered sugar will dissolve very easily. The sugar cube, because it hasn't been mashed up enough, it's going to take a little bit of time. So solubility is affected by degree of subdivision. Okay, degree of agitation. Agitation is just stirring. If you stir, it's going to get dissolved. If you don't stir, it's going to just sit there. It'll dissolve eventually, but it won't dissolve as fast. All right. And then temperature, we've already kind of discussed that. If you're putting sugar into cold water versus hot water, the hot water and you stir a little bit, it'll be all dissolved. So as you increase the temperature, it's one of the factors that affects solubility. Okay, now we're ready to move into which compounds are soluble and which are not. Now we've already said that ionic compounds that will separate out into ions will be soluble in water, and then water will just create these hydrated ions and suspend them. But not all ionic compounds are actually soluble in water. And obviously, I already told you not all covalent compounds are soluble in water, only the ones that can hydrogen bond with water are soluble. So right now we're going to focus on ionic compounds that are soluble in water. And since not all of them are soluble, we need a guideline. We need a table to help us out. And you have a table in your book. It is table 8.2. This is it. Okay, can you guys see it? Table 8.2. It says solubility guidelines for ionic compounds in water. So I'm going to put this up here because we're going to have to refer to it. Now, in higher level chemistry classes, you pretty much have to know all this yourself. I don't know why there's that sound. Okay, there we go. In higher level chemistry classes, you pretty much have to have this all memorized. In this class, you just observe the table, look at the table, have it handy with you when you're taking a quiz or a test or whatever, so that you can, it's like your really cool, completely legal cheat sheet, okay? This is the solubility guidelines for ionic compounds in water. And this is the way you're going to know if a compound is soluble in water or not. So let's try to read the table together. You should get yours from your book, print it out, do something so that you know how to follow along. Okay, so it says here, let me get my glasses, that compounds containing the following ions are soluble with the exceptions noted. So group 1A, so anything in group 1A, if you see that in an ionic compound, it's going to be soluble. So if you have a lithium nitrate, for example, or you have a sodium chloride, or you have a potassium iodide, these are group 1A, group 1A, group 1A. Or if you have a, what else is in group 1A? I should have all this stuff memorized here. Cesium sulfate. Okay. Any group 1A. Any group 1A. Why did I put two cesiums here? Because cesium's +1, sulfate is -2. So long as you see a group 1A, it's going to be soluble in water, okay? Also, anything that has an ammonium, if you see an ammonium ion, it doesn't matter what it's attached to, but you see an ammonium ion, ammonium chloride, ammonium phosphate, any ammonium ion, you see that, it's going to be soluble in water, okay? Acetate. That's a polyatomic ion that I didn't talk about, but again, if you ever see that acetate polyatomic ion, they are all soluble in water. Nitrates, all soluble in water. Chlorides, bromides, iodides, all soluble in water, but there's an exception. If they're connected to silver, lead-2, or mercury-1, they're not soluble. So what do I mean by that? So if I have calcium chloride, sodium chloride, silver chloride. According to this rule, all chlorides are soluble unless they're hooked up to silver, lead, or mercury. This one is mercury 1, because remember, mercury 2 would just be Hg2 plus mercury. 1 has 2 mercuries attached to each other with an overall charge of +2. So these are the exceptions to the solubility of chlorides. So according to this is going to be soluble, because calcium's not an exception. This is soluble because obviously group 1A is always soluble. This one, because according to this, anytime a chloride is attached to silver, it is insoluble. Okay? All right, in the next video, we'll finish up the solubility rules and we'll do a little bit of practice, and then we'll be able to move on to other things.